Okay, so we're going to make a video reviewing the iGCSE specification for the thermal physics and density topic areas. So we're going to start off with density. So first of all, state an equation to calculate it and identify the symbols and units that we need. So the equation is density is mass divided by volume. The mass is typically measured in kilograms, the volume in meters cubed, giving us density in kilograms per meter cubed, and that's often written as a symbol equation where density is rho, mass is m, and volume is v. You do occasionally see density asked for in grams per centimeter cubed or something like that, so you just have to be a bit careful with your units sometimes. So describe an experiment to determine the density of a liquid. So the problem with a liquid is it flows, so we're going to need some sort of container. So we would probably use a measuring cylinder. So what we want to do is determine the mass of the liquid. So we're first going to measure the mass of the empty measuring cylinder, and we'd measure the mass of the measuring cylinder containing a certain volume of liquid, and the measuring cylinder allows us to measure what that volume is. And then we can get the density using the mass difference, so the difference between the full and the empty cylinder divided by the volume of the liquid there. So we've got a diagram to basically illustrate how that works. So we've got the full measuring cylinder on the left that we'd measure the mass of using a mass balance. We've got the empty one in the middle that we'd measure using a mass balance. If we find the difference between their masses, that should be the mass of the water or whatever liquid we used. So describe how the experiment would change if we determine the density of a regularly shaped solid. So what we would do, we'd still need to measure the mass using a mass balance, but we would find the volume by measuring the dimensions of the object. And for small objects, we want a measuring device like a micrometer or a vernier calipers, and we'd use those dimensions to figure out the volume there. So describe how it would change if the solid were irregularly shaped, so measuring its dimensions isn't going to give us the volume. And we also need to factor in what happens if its density is less than water, which can be problematic. So first of all, you measure out a volume of water in a measuring cylinder, and the volume needs to be big enough that you can completely submerge the object you're interested in that. And then what you'd do is you'd measure the volume change when the object has been fully submerged. And if you have an object that floats, you may need another object to hold it underwater as part of the experiment there. So that's how you can deal with low densities. You can pin it down with another heavier object. Okay, so just to show you a couple of devices I've referred to, the micrometer is the top left and a vernier caliper is the bottom left. So these are devices which are more precise for measuring small dimensions. And then, as we were saying, to get the volume of an irregular shaped object, what we do is we submerge it under liquid, it will probably be water, and we're interested in the volume change because that would be the volume of the object. Okay, so just looking at describing how we can determine whether an object will float, nice and simple. Objects that are less dense than the fluid will float. Objects that are more dense will sink. That's straightforward enough. And you can see a nice illustration of that. What we've got here is liquids stacked up on top of each other because they're decreasing in density as you go up, so that each of those liquids is floating on the other ones there, which is a nice demo. Okay, so moving on to looking at pressure. State an equation to calculate pressure, identifying any symbols we've used and the units. So pressure is force divided by area, pressure in pascals, force in newtons, and area in meters squared. And that is usually simplified to this equation here, P equals F over A. So we're going to sort of use this idea of pressure to describe how we can measure pressure using a barometer. Okay, so a barometer looks a bit like this. What you have is a liquid, usually mercury, and we can see that has gone up the central tube and is open to the atmosphere at the bottom. So what happens is if air pressure rises, it acts over the area exposed to the air. So where you can see the arrows acting there. So what that means is there's now a force to accelerate the mercury upwards. So it's going to push the column of mercury higher. So as the height of mercury increases, the weight force of that column is going to increase until that weight force balances the new higher pressure. And all we do is we take several known pressures and mark the height of the mercury at those pressures, and that's what allows us to figure out or use this device to measure other pressures. Okay, so I've used this word a couple of times, so let's just quickly identify what a fluid is. A fluid is just a word used to describe both liquids and gases combined. So whenever I use the word fluid, that means it could apply to either liquids or gases. So state the equation to find the pressure at a certain depth below the surface of a fluid, again looking at symbols and units. So this is the equation. Pressure is density times gravitational field strength times depth below the surface of the fluid, measured in pascals, kilograms per meter cubed, newtons per kilogram, and meters respectively. So why is it that the pressure increases the deeper you are? So the key thing is the weight of water above the position that you are at. So the deeper you are, the greater the weight of water is above you. So that's why we've got higher pressure, we've got a larger weight force. But if you use a denser fluid, again, the same volume above you would have a bigger mass and therefore a bigger weight. So again, that's what would increase the pressure that you feel. Okay, so just looking at a bit of an extension thing here, seeing if we can actually show something that we've used. So by finding the pressure above and below a prism-shaped object, and all that means is constant cross-sectional area, show objects float if they are less dense than the fluid they are displacing. So what we've got in here is an object with certain dimensions that I've labelled in some kind of fluid which I haven't named at a depth h below the surface. So what I'm going to do is figure out the volume of the fluid above the top surface and the volume of the fluid above the bottom surface of the object. And that's those expressions there. A is the cross-sectional area. I can only draw a 2D image, but A is there to represent the cross-sectional area. So the volume is going to be the area times the height of, so we're calculating the volume of the fluid above the top surface, and that volume is going to be slightly more above the bottom surface because you've got this extra distance. So then what we're going to do is calculate the weight of water above each of the surfaces, and mass is density times volume, and then weight is mass times gravitational field strength. So putting those things together gives us these expressions here. Okay. So what we're going to do next is calculate the pressure on each of them. So using the force and dividing it by the area it acts over, we can get expressions for the pressure at the top and the bottom surfaces. Using those two expressions, we can find the pressure difference, which is just density times the gravitational field strength times the actual height of the object. And using that pressure difference, we can calculate the upwards force. Because where there is a pressure difference, there'll be a force to get rid of that pressure difference. So substituting in for the pressure, we get the expression there. And the thing to spot is that the area times delta H is just the volume of the object. So this force we call upthrust or buoyancy, and we can calculate it if we know the density of the fluid there, the gravitational field strength, and the volume of the object. Okay, so the weight force of the object, the force downwards, is going to be the mass times gravitational field strength, and mass is density times volume, but this time it's the density of the object, not the fluid there. So if the object floats, there must be a resultant force upwards. That's what brings it back up to the surface of it. So we know the upwards force must be greater than the downwards force. The g's cancel out, the volume of the objects cancel out, and we get left with an expression that density of fluid must be greater than the object for it to float. And we get it the opposite way round if the object sinks. So if it sinks, weight force must be less than upward force. Let's reflip that around. So weight force must be greater than the upwards force, and therefore we get the opposite condition there, and that's why density is important. Okay, so we're going to explain how a manometer works. So first of all, a manometer is a device to measure gas pressure. And it does it by comparing it to a known pressure, usually atmospheric pressure. So that's what we're trying to do. And the way we actually take a measurement is we measure the height difference on either side of the manometer. And the bigger the height difference, the bigger the pressure difference between the two sides. So we want to know if we want to know what the unknown pressure is, we'd need to know the fluid density that we've used. We need to know the height difference between those two, and then we could calculate the pressure difference. And just incidentally at this point, we could change the sensitivity of our manometer by selecting an appropriate fluid. So if you use a less dense fluid, you get a bigger height change, which means it's more sensitive, but that is at the sacrifice of reduced range. But we'll talk about that a bit more later on. Okay, so moving on to the molecular model of matter. State the distinguishing properties of each of the three main phases of matter. Okay, so solids have a fixed shape and volume as long as no force is applied and temperature is constant. Liquids have a fixed volume, but their shape can change to match the shape of the container. Gases can change either their shape or their volume to make sure they completely fill a container. Describe the molecular structure of solids, liquids, and gases in terms of arrangement, separation, and motion. So in a solid, they are packed very close together, which means the separation is very small. And this leads to there being very strong forces between the molecules, which hold them tightly in a regular pattern, and that means they can only vibrate. Whereas in a liquid, the particles are less close together, and that means that the separation is larger, in other words. So the force between the molecules is smaller, and that means they are free to move past one another, so their arrangement is completely random. In a gas, very much similar story, but they're even further apart, so the force between the molecules is really, really small, and that allows them to move freely past one another, and so they are also arranged completely randomly. Okay, so delving into the relationship between temperature and molecular motion. So temperature is a measure of the average kinetic energy of molecules. So in fact, temperature and average kinetic energy are directly proportional, but incidentally, that's only if you measure the temperature in Kelvin that they're directly proportional. Average kinetic energy varies linearly with temperature in degrees Celsius. We'll talk about what the difference between those relationships is a little bit later on. So explain how gas particles exert pressure on a container. Well, what's important is the collisions between gas molecules and the container. So during a collision, the gas particles experience a momentum change because their direction changes. And so in the process of a momentum change, the gas particle exerts a force on the walls of a container. So if we can increase the momentum change during a collision, or if we can get more collisions per second, we can increase the pressure of the gas. So explain why changing the temperature can lead to a pressure change. Well, increasing the temperature increases the speed or kinetic energy of the molecules, and that means the momentum is bigger incidentally. So in each collision, there's a bigger momentum change, and if they're traveling faster, they're going to collide with the walls more often, so we get more collisions, both of which increase the pressure. So explain why changing the volume of a container can lead to a pressure change. Well, if you increase the volume, the number of collisions per second would decrease because particles have to travel further before they collide with the container again. And it also increases the area over which the collisions are spread, both of which decrease the pressure. So why changing the number of molecules can lead to a pressure change? More molecules means there are more collisions per second. That's going to increase the pressure. Okay, so I talked about a directly proportional relationship earlier, so let's be specific about what that is. So a directly proportional relationship can be described in two ways, really. Either we describe it as a straight line through the origin, or we can say the y-coordinate divided by the x-coordinate of any point on the line is a constant. So those would be the two ways you can describe directly proportional. They both end up with exactly the same graph. Okay, so Inversely proportional, which I'm going to talk about in a second, is slightly different. So one way of describing it is you get a graph that looks like this. Or another way of doing that is if you take the reciprocal of one of the quantities you put on the axis, it's a straight line through the origin. Both of these graphs show an inversely proportional relationship. So the mathematical way of expressing it is the x-coordinate times the y-coordinate of any point on the first graph is equal to a constant there. So the best way to identify it is an inversely proportional relationship is plot the reciprocal of one of the quantities on the like 1 over x on the x-axis, but we can also show x, y as constant there. Okay, so why are we talking about inversely proportional? Well, one of our important laws is inversely proportional. So Boyles Law states that for a fixed mass of gas at constant temperature, the pressure and the volume are inversely proportional. So what does that look like? Well, it's the pressure times the volume are a constant. So I've taken that straight from the relationship I've just looked at. Okay, so that's Boyle's law, but the form we often see is the initial pressure times the initial volume is equal to the final pressure times the final volume. Okay, so that's Boyle's law, and we might need to rearrange that equation to solve for an unknown, for example. So next we're going to look at why materials expand when they are heated. Well, when molecules are attracted to one another by the electric force, which is what holds them together in a structure, if we want to move them further apart, we have to supply energy to do that because they don't want to move apart. And what we say there is we're increasing their electric potential energy if we pull these particles which are attracted to one another further apart. And one way of doing that is heating, so supplying thermal energy, which allows the electric potential energy to increase, which means the separation of the atoms or molecules increases. Okay, so if we heat solids, liquids, and gases, they expand by different amounts when we do that. So in a gas, the force between the molecules is really small. So if we supply them with some energy, they expand a lot. The magnitude of the expansion is really big. Whereas solids, the forces between the molecules are really big. So when we supply them with energy, their expansion is actually pretty small. But incidentally, at this point, since we're talking about it, when a solid object expands, although it doesn't expand very much, the force of its expansion is massive, which can have certain effects, like when you're designing bridges, you need to account for the temperature changes throughout the year. Same with railways, we need to account for that as well. Okay, so moving on to another type of relationship, which I mentioned already, a linear one. So a linear graph looks like this. So it's a straight line, but it doesn't go through the origin. That's its characteristic there. And this often gets described in the form y equals mx plus c, where m is a gradient and c is the y-intercept, and those have fixed values for any y or x. Okay, so moving on to something I mentioned earlier. So I was talking about the sensitivity of the manometer, and I said if we used a less dense fluid, that would be a more sensitive measuring instrument. So what is sensitivity? Well, it's the change in reading of a measuring instrument divided by the change in conditions. So a manometer, you get a height change, so that's the change in reading, and the change in conditions will be the difference in the pressures from before and after. So sensitivity is highly linked to range, so we're going to talk about that too. So range is the largest reading you can take with a measuring instrument minus the smallest. And the reason I put the two together is increasing one always or generally acts to decrease the other. So the more sensitive you make a measuring instrument, the smaller the range of possible measurements you can take with it. So there's always a trade-off. Okay, so explain the process required to design a thermometer. So thermometers are almost exclusively based on two fixed points, and we have agreed fixed points, so all thermometers work the same. So the two fixed points that we use are the boiling point of pure water, which is 100 degrees, and the melting point of pure ice, which is 0 degrees. I'm going to talk a little bit about what boiling and melting mean later on. So essentially what you do is you get your glass tube, you put whatever liquid you want to into it, and you stick it in melting ice, and you mark the height of the liquid in that. You then put it in boiling water, and it's going to expand when you do that, and you mark the height at 100 degrees, and then all you do is then divide the difference between those into 100 divisions, which we decided to call degrees, and then you have constructed yourself a thermometer. Okay, so how can we change the sensitivity of a thermometer, and what are the consequences of doing that? So one change we can make very easily is change the cross-sectional area. So if we change the temperature, the liquid expands. But if the thermometer is narrower or has a smaller cross-sectional area, that results in a bigger height change. So the change in height for the same temperature change is bigger, which means it's more sensitive than it was with a wider one. But the issue with doing that is then you're going to get a smaller range of measurements you can take, because the temperature at which it goes off the top of your thermometer is going to be much smaller if it's narrower there. So that's the trade-off there. Okay, so to talk about another device we can use to measure temperature, a thermocouple. So essentially a thermocouple is two metals which are connected together, and then also to a voltmeter. So the part that you put in the thing you want to measure the temperature of, you call the hot junction. So it's just called a junction on here. And then you have the other end of it in a reference temperature, which is often room temperature, or we could stick it in ice if we want an even more fixed cold temperature. And then what we do is we have that connected to a voltmeter. So those are our three parts. We need a hot junction, we need a cold junction between the two, and then we need a voltmeter there. So what are the advantages of a thermocouple? Well, what we want from them is we get a faster response time. So the condition that a thermocouple relies on changes much more quickly in response to temperature changes. So for instance, if we want to measure temperature changing over time, we would use a thermocouple. And the other advantage is we can record much higher temperatures, because liquid thermometers are based on or limited by the boiling point of those liquids, whereas this uses metals, and metals typically have a very high melting point, so we can measure much higher temperatures. All right, so we're just going to go into a little bit more detail on how a thermocouple works for those of you that are interested in. So we're going to start by looking at what a potential difference is, because that's what our voltmeter is measuring. So in terms of charge, potential difference is created by having a difference in charge between 2 points, sometimes called a charge gradient. So potential differences are often created by one region having a positive charge and the other region having a negative charge. But it can also be one having a more negative charge than the other, which is what it is in this case. So in a thermocouple, what's happening is this is based on electron diffusion. So free electrons diffuse from a hot region of a metal to a cooler region, but different metals have different diffusion rates. So if you have a high diffusion rate, you're going to get a buildup of electrons quicker than something with a low diffusion rate, and that's where the potential difference comes from that you can measure using the voltmeter. Okay, so moving on to look at thermal energy in a bit more detail. So first of all, we're going to define some terms that we've been using or will be using. So we talk about the internal energy of a material, which is the sum of a system's kinetic and potential energy. So we take the kinetic and potential energy of every molecule and we add them all up, and that gives us internal energy. Kinetic energy is the work we have to do to accelerate an object from stationary. So when we increase the speed of an object, we're effectively storing energy in its motion. Electric potential energy is the work done to separate two charged particles that are attracted to one another, because they don't want to move apart. So if we want to make them, we have to do work. So What is the impact of supplying or removing thermal energy on the internal energy of a system? Well, if you supply thermal energy, that increases internal energy, and it does it one of two ways. It can either increase the kinetic energy, which means temperature rises, or it can increase the separation, which means electric potential energy rises. And we'd go from a solid to a liquid to a gas, so we're going up the phases of matter, if you like. If you remove thermal energy, that decreases the internal energy, so that can either decrease kinetic energy or decrease temperature, or it can decrease separation and it go down the phases the opposite direction. So to model temperature changes, we use terms like specific heat capacity and thermal capacity. So thermal capacity is the energy required to increase the temperature of a material by 1 degree. Specific heat capacity is the energy required to increase 1 kilogram by 1 degree. Specific usually means per kilogram in any situation. So the equation that links the two is thermal capacity can be calculated if you know the mass of something and the specific heat capacity. So we can measure the specific heat capacity of a material using quite a simple experiment. So what we do is we have an electrical immersion heater. We need a voltmeter, an ammeter, a power supply and a thermometer, and then a block of whatever we're trying to measure. So we need to know the mass of the block and the initial temperature of the block, because we're going to need to measure the temperature rise. We're going to switch on the heater and record the potential difference in current, because that will allow us to work out the power being delivered. So using a data logger, we can continuously measure the temperature at different moments in time. So I would use a data logger here, which is effectively a thermocouple. Then what we're going to do is we're going to calculate the thermal energy supplied to the block using energy is equal to power times time. And here we are assuming that all the energy that we produced is going to the block. So what we're going to do is we're going to plot a graph of thermal energy supplied against temperature rise, or delta T, which should look a bit like this. And from this graph, we're going to measure the gradient of the line, divide it by the mass, and that would give us the specific heat capacity. Okay, so we're going to use the equation that allows us to link thermal energy and temperature rise. That looks like this one. So Q is the thermal energy, which you measure in joules. M is the mass in kilograms, and delta T is the temperature change measured in degrees. That can be Celsius or Kelvin, it doesn't matter. So the only thing that we haven't looked at is C, which is the specific heat capacity, and we can figure out its unit using the equation. So C is going to be Q divided by M delta T, so it's going to be measured in joules per kilogram degrees Celsius. Okay, so that's temperature change. Let's start having a look at phase change. So two of the ways to describe phase change are melting and boiling. So melting is when you turn from a solid into a liquid at constant temperature by supplying it with thermal energy. Boiling is when you turn from a liquid to a gas, again at constant temperature. So what is the significance of these points? Well, it's the temperature at which the average molecule has enough energy to change phase, whereas below the boiling point or melting point, the average one wouldn't have enough energy to change. So describe in terms of molecules the process of solidification and condensation. So solidification is when you remove energy, and that causes the particle separation or the electric potential energy to decrease, and that's a lot. So in terms of solidification, it's to change from a liquid to a solid, whereas condensation is the same but changing from a gas to a liquid. Again, all of these at the moment are at constant temperature processes. The one that isn't at constant temperature is evaporation, which is why we'll look at that now. So this is when high energy molecules actually can escape from the surface of a liquid, but at a temperature below the substance's boiling point. So this isn't a constant temperature process, which we'll look at now. Okay, so we're going to look a little bit more detail at the difference between evaporation and boiling, so we can be clear on them. So Boiling is when you're heating a liquid or supplying thermal energy, and it turns into a gas at constant temperature, and that temperature is called the boiling point. So for water is 100 degrees. Evaporation is when molecules gain sufficient energy to escape below the boiling point there, and that's not a constant temperature process, which we'll talk about. So in terms of what's going on with evaporation, so molecules of a substance or a liquid, gas, whatever it is, have a range of kinetic energies, some high, some low, and mostly in the middle. So during evaporation, a high kinetic energy molecule on the surface, and it does have to be on the surface, is what escapes, and we'd now consider it a gas. So what does the evaporation do to the liquid left behind? Well, it decreases its average kinetic energy because you've lost one of the high energy particles. And we know that average kinetic energy is linked to temperature. So that means the temperature of the liquid left behind has decreased. So this isn't a constant temperature process. Okay, so what can we do to increase the rate of evaporation? There are 4 factors really that we can think about. If we increase surface area, liquid temperature, or airspeed above the liquid, those would all increase the rate of evaporation. And if we decrease the humidity, or the amount of water contained in the air already, that would also help us. So in terms of how those work, just digging into those a bit more. So if you have a higher surface area or a higher surface temperature, that gives you a higher chance that there is a high energy molecule on the surface. Increasing temperature creates more high energy particles, and having a larger surface area means there are more particles on the surface. So both of those increase your chance of having a high energy particle on the surface. Higher humidity makes it harder for evaporation because the air already contains lots of water. So the reason that airspeed helps with that is it acts to decrease the humidity above the liquid, and that increases your rate of evaporation. Explain how an evaporation of a liquid leads to a material in contact with the liquid decreasing in temperature. Well, what we're also asking is, how does sweating work? Same thing. So the first thing to always remember is thermal energy moves from an area of high temperature to an area of low temperature. So that's going to be important. So evaporation, if you remember, decreases the liquid temperature, and that means it's going to be decreased below the temperature of the material it's in contact. So what's going to happen is thermal energy flows from the hot material, so let's say during sweating that's us, to the cooler liquid, that's the water on your skin, and that decreases the material's temperature, essentially. Okay, so looking at phase change in a bit more detail, we're going to look at the 2 latent heats. So latent heat of fusion, the energy required to change 1 kilogram of material between solid and liquid phases. And latent heat of vaporization, the energy required to change 1 kilogram between liquid and a gas phase. So we're going to talk about what latent heat is there to model. So latent heat is there to allow us to link thermal energy to electric potential energy, because that's what's changing when we're changing phase. So essentially what the latent heat allows us to do is work out how much energy we have to give to a kilogram to make its electric potential energy big enough that we've got a phase change. And the equation that we use is Q equals mL. Q and M we've met before in terms of the symbols, but L is the only new one, which is the latent heat measured in joules per kilogram. So we can do an experiment to determine the latent heat of a material. We can have an apparatus something a little bit like this. So what we're going to do is we've got an immersion heater again. This time we've got ice here. So what we do is we connect the heater to an ammeter and a voltmeter. Again, we want to measure the power. Then what we're going to do is we're going to measure the time taken to melt a determined mass of ice. So we'd have measured the ice beforehand, and we're going to measure the time it takes to melt all of it. And you can see that in this situation, once the water is melted, it's going to fall through the funnel, and then we are just going to focus on giving the energy to the ice remaining. So to get the latent heat, we do power times time, which is the energy we've supplied, divided by the mass, and that's found us our latent heat, in this case the specific latent heat fusion of ice. Okay, so now looking at transferring thermal energy. So one way we can transfer energy is by conduction, and different materials have different levels of conductivity. So if we want to compare them, the first thing we need to do is we want to make sure that everything apart from the material is the same. So we want the same dimensions and the same amounts, those kind of things. And then what we do is we put all of them in a hot region. So we might put them into a Bunsen burner, we might put them in hot water, as long as they're all exposed to the same temperature. And then what we'd do is we'd measure the time it takes for thermal energy to reach the opposite end. Because the faster thermal energy travels, the better it is as a conductor, or the higher the conductivity is. Okay, so in terms of how conduction works, at a very simple level, it's due to the collision of particles. So if you heat the molecules in this case on the right-hand side, they will get higher kinetic energy. They'll collide with the molecules next to them and pass that energy along the material. So in terms of what makes a good conductor, first of all, being solid automatically makes you a better conductor because your particles are all packed closer together, so the energy travels faster through the material. And to make you even better than that, a metal tends to be a very good conductor, and that's because what makes metals special is they have free electrons, which can transfer the energy even faster there. So why are liquids and gases bad conductors? Well, it's because the particles have a bigger separation. So you get less frequent collisions, so it takes longer to transfer energy by conduction, and other processes do it much faster. So one of those processes would be convection. So what happens in convection is the molecules directly above the heat source rise, and they're replaced by the molecules from a cooler region of the fluid. So that's generally speaking what's going on with the molecules. So let's have a look at why that is. So we're going to be talking about upthrust and density, which we met earlier. So when we heat it, the separation of the molecules of a fluid increases, so the density decreases. So when a density is lower than the surrounding fluid, as we saw earlier, the upward buoyancy force is greater than the weight force. So the molecules will accelerate upwards, and that leaves a space for the cooler ones to move into. So convection works very well in gases and liquids, but it doesn't work in a solid. And the reason being, as we saw earlier, the molecules in a solid are not free to move around. The forces between the molecules are very strong. And to have convection, the molecules need to be able to move. Okay, so looking at the final energy transfer mechanism, we've got what we call an electromagnetic wave. So in terms of its key principles, these waves act to transfer energy from a high temperature region to a low. And as they travel, they cause oscillations in electric and magnetic fields. So you can see their impact as they travel through. But what they don't need is particles, so they don't oscillate particles, and therefore they can travel across the vacuum of space, which is why they can reach us from the sun, for example. Okay, so in terms of how the radiation changes with the temperature of the object emitting it, higher temperature objects emit higher frequencies of electromagnetic radiation. And in terms of how that's relevant, so on Earth, the temperatures are about the right level to produce infrared, the infrared section of the spectrum, which is why we usually describe it as infrared radiation in terms of energy transfer. Okay, so different types of surfaces are better or worse at absorbing or reflecting radiation. So if you are a matte black surface, you'll be a very good absorber or a very good emitter of radiation. And if you're a white, shiny surface, you're going to be very good at reflecting. And those processes are the opposites of each other. So white, shiny are rubbish absorbers and emitters, and matte black are rubbish reflectors. So how could we actually illustrate this? Well, what we'd need is a set of identical objects, which the only difference is the surface. And then what we would do is we place them an equal distance from a heater and measure the temperature of them over time. And based on what we've seen, we'd expect that matte black coloured one should be at a higher temperature when heated for the same time, because it's a better absorber of infrared radiation. So it's not just the surface that affects the rate of radiation emission. There are a couple of other things too. There'd be the surface area and the temperature of the object. If you have a bigger surface area or a higher temperature, you will have a greater rate of emission. And again, going a bit beyond the course here, what you come across later in physics is there's a really nice law that links all these things together. So the rate at which you emit energy, or the power, can be calculated with four things. There's a constant, which is just as a value, so that's not going to change. The emissivity of the material, or how good an emitter it is that epsilon there. The surface area, and we have temperature measured in Kelvin to the power of 4. So we can see that the temperature plays a really big role in the amount of energy emitted, but so does the area and so does the surface. And that brings to a close this video on thermal physics.